Now, by this point in class, we discussed a few different examples of thermodynamic processes. How we went from state A of a gas or a thermodynamic system to state B. The process is that transition. But most of these have been somewhat random affairs. We want to focus now specifically on 4 specific types of thermodynamic processes that we want to understand in much greater detail. So as a reminder, if I have a PV diagram here, every point on this PV diagram is a specific state of the system at which we're looking at. So every point represents a combination of pressure, volume, and temperature. And the thing is that we have infinite possibilities to go to all these different states along all these different paths. And every path represents a different thermodynamic process. But as you can see, that can get real confusing real quick. So we're going to focus on these specific 4. And in particular, we're really going to focus on these questions. For each process, what stays constant and what changes? How can we physically accomplish this thermodynamic process? So I have a piston. How can I physically make it go through this process? How does a PV diagram change while the process is taking place? And lastly, how can we relate this process to the first law of thermodynamics? Delta U equals Q plus W. The change in internal energy equals the heat plus the work. The first type of process we're going to look at are what are called isobaric processes. Now, isobaric, specifically, we have this prefix here, iso, which means same or equal. And baric essentially refers to pressure. Think a lot like barometer. A barometer measures pressure. So an isobaric process is a constant pressure process. The pressure should be the same the entire time. Now I'm going to start here with a piston. And in this piston I have a gas. And we're going to say that the piston, this may sound a little weird, is massless and free to move. So what does that mean here? Well, why first is the piston balanced in the first place? Why isn't it moving if it's massless? Well, remember, however much force we get applied to the piston from these particles, now that's distributed over an area in the form of pressure, that must be balanced out by whatever particles are out here in the environment, in the atmosphere. And the reason why we consider this massless is we don't want to have to think about these particles having to gain extra momentum to overcome the weight of the piston head. So we're going to go ahead and say that the only reason why this piston will move back and forth is essentially due to the balance of the pressure inside and the balance of the pressure outside. More pressure in, it's going to move out. More pressure out, it's going to move in. So looking at this specifically, I want to think about a way, how can I make this expand outwards? Well, and keeping the pressure constant. Well, to do this, I'm going to apply some heat. I'm going to heat up this cylinder. That's going to cause the particles inside to move faster. They're going to hit the barrier with a greater amount of force because they're undergoing a greater change in momentum. So therefore, that force distributed over this area will be a greater pressure, and that's going to push outwards. And that is therefore going to cause an expansion. But every time it pushes outwards a little bit, naturally, it's going to be continually balanced a little bit on the way, so that pressure is going to stay the same. So if I have my PV diagram here, see, I'm going to start here at pressure. Now I'm going to go this way because the pressure stays constant as it expands. So this is what we call an isobaric expansion. I heat it up and the gas naturally expands and it increases, it basically pushes the piston to keep those pressures balanced, to keep the pressure the same. Similarly, I can have, well, what if I want to go the other direction? What if I want to go this way? What happens if I want it to compress at a constant pressure? Well, instead of adding heat, I'm going to cool the system down with an ice bath or ice or something along those lines. That's going to cause these particles inside to move slower. Particles on the outside are going to be moving faster, and it's going to push it in to try to equalize those pressures. So this would cause, I'm going to start here. Once again, pressure is constant. My PV diagram is going to be a horizontal line. That was not drawn real well. A horizontal line to the left as it compresses. All right, so let's analyze this in a bit more detail. For both of these, an isobaric expansion and an isobaric contraction, the pressure stays constant. But that means that the V changes, and we can see that here because we're expanding it here, and here we are compressing. And the T is additionally not constant. Because if we look, if I'm moving this way, remember that means the temperature is going up. So as we had heat, the temperature inside increases as the volume increases. And in this situation, the temperature is going down. Now, going from there, though, this connects to that if we have a change in temperature, we also have a change in internal energy, which we know through this equation, delta U equals 3/2 nR delta T. So if we know that delta T, which we can find by just comparing 2 points, either with the ideal gas law or the combined gas law, we can figure out the change in internal energy during this process. And that must be equal to, due to the first law of thermodynamics, Q plus W. Well, how can I separate Q plus and W here? Well, remember, we talked about this in our last lesson, that this area here is the work. Similarly, this area underneath this graph is the work. And if I look, this is P, because this is the pressure from 0 to P, and this would be delta V from your initial volume to your final volume. Similarly, I have P and delta V. So our work is actually going to be equal to P times delta V. But notice, we have to put a negative sign here. And why is that? Well, if we look in this top situation, as it expands, as the volume grows, remember that means that the gas is losing energy to the surroundings as work. So even though delta V is going up, the amount of energy, the work, is actually going down. So we have to put this negative here. Similarly, if it compresses, that means the surroundings are doing work on the cylinder, and therefore, even though delta V is going down, our mechanical work on the system is going up. So I want to be real careful here. This is a very specific equation. It's actually on your equation sheet. W equals negative P delta V. This is the only situation in which this equation applies. A very common mistake is to try to use it in the other different processes, and that's not going to work. Pressure has to be constant for this equation to work. So if I want to figure out Q, for instance, I could figure out delta U from this graph. I could calculate W. I could stick both those in, and that would allow me to determine how much heat was transferred to the system or away from the system. The second type of process we're going to look at is called isovolumetric. So remember, once again, iso means same or equal. So this is telling us same volume. This is also called an this is pronounced isochoric process, where choric means space equal volume, same idea. So these are thermodynamic processes in which the volume is constant. Well, how can I keep the volume constant with this piston? Well, the easiest way to do it is basically make it no longer a piston. Essentially, we're going to just make it a cylinder, because we're going to lock the head of the piston in place so it cannot move back and forth. So no matter what, the gas is stuck in this volume. But we're going to go ahead and heat it up. And if we do that, well, if we heat it up, the volume can't change, but we're definitely going to be increasing the pressure. So we're going to get a graph that looks something like this. It's going to go straight up. Similarly, I could have a situation where instead of heating it, once again, I'm going to lock the piston in place, but instead I'm going to cool it. And now the pressure is going to go down. And once again, there's going to be no change in volume. So both of these, this would be an example of like isochoric heating or isovolumetric heating, and this would be isovolumetric cooling. So let's look at the specifics of the situation now. The pressure is not constant, as we can see. It's going to change based on the fact that we're either heating up the system or cooling it down. The volume stays constant, but the temperature does not. In this situation, it goes up. This situation, temperature goes down. And once again, if the temperature changes, that lets us know that the change in internal energy is going to change, and we can use the equation 3/2 nR delta T. So once again, we can use this delta T with the graph to determine the delta U. Now let's look at this last part. Delta U equals Q plus W. Well, the thing is here is we said work is the area under these graphs, but these are vertical lines, so there is no area. And if there's no area, that means our work here is going to be 0. Because there is no expansion or compression, all of this situation, all this process, the only change comes instead from heat. Work is not a factor here. So delta U will just equal to Q. And in fact, another way to think about these processes, isovolumetric ones, is that it is all heat, no work. No expansion or compression, just absorbing heat or releasing heat, thermal energy. So we've discussed constant pressure processes, isobaric, and constant volume processes, isovolumetric. So it's probably not that surprising that our third process is going to be isothermal. In other words, constant temperature. Well, how exactly can we do a process that is constant temperature? So once again, I have my piston. The head of the piston is massless and free to move, so it can go back and forth naturally. And what I'm going to do actually is I'm going to stick this entire piston in what is known as a heat sink or a heat reservoir. Now, that sounds very fancy. What that really means is I stick the piston essentially in a tank of water. And there's a specific reason for that, because now I am going to slowly, let's make this a little easier to see. I'm going to slowly pull this piston open. And when I slowly pull it, this temperature is going to go down as it expands. So to keep the temperature constant, the piston is actually going to absorb heat from the water. And the reason why this works so well is water is really good at holding a lot of heat and not having a huge change in temperature. So essentially, as you expand this cylinder to match the temperature of the tank of water, it is going to pull some heat in. And the process is going to look something like this. It's going to go kind of down at kind of a curve. And I could similarly do the same thing in the opposite direction. So if I have a piston once again in a heat sink or heat reservoir, you can slowly, let's make this easier to see again, we can slowly push the head of the piston in. And that's going to cause the temperature in this to go up as it's compressed. And therefore, to keep the temperature constant, heat is going to naturally flow. Thermal energy is naturally going to flow from the piston to the water, where it will be absorbed without much temperature change. And that is going to look something like that. It's kind of a curve upward. So, the pressure is not constant, the volume is not constant, but the temperature is constant. And that's slowly pulling and pushing what's important there, because you have to go slow to make sure that the temperature has enough time to reach equilibrium. Additionally, because there is no temperature change, that means we have no change in internal energy of the system. The gas is going to keep the same amount of internal energy. So if I look at delta U equals Q plus W, well, now delta U is going to go away because it's going to be 0. And so we're going to be left with Q is equal to minus W. In other words, as I expand it, it is doing work on its surroundings, but it gains an equal amount of energy from heat from the water. If we compress it, we are giving the gas a certain amount of energy, and it's going to release that amount of energy as heat to the surroundings. The work and the heat are going to constantly be balanced. The fourth and final process that we're going to really focus on in detail has a bit of a crazier name. This is pronounced adiabatic. It's an adiabatic process. And instead of having all heat, no work, now we're going to have all work and no heat. So how can I cause this to expand or compress without having any heat exchange? And the easiest way to do that is we're literally going to just put this piston in some sort of insulation. This could be in a huge thing of styrofoam. It could be in like some sort of thermos, something to keep it really, really insulated from its outer surroundings. And what I'm going to do now is I'm going to rapidly pull this out rather than slowly. And that rapid pull is going to cause a really quick expansion, and the temperature is going to really quickly drop. So what's going to happen here is going to look something even more severe than the last one, like that. Once again, it's kind of a curve. We're going to look at those in a little more detail in a second. And additionally, we can go the other way. I have a piston again. I insulate it so that there can be no heat exchange with the environment, and you rapidly push it in. You basically just rapidly compress it, and you do it so quickly that no heat has time to leave. And doing that, I'm going to rapidly increase the pressure and decrease the volume, and we're going to get something looking like that. So in this situation, none of the factors are constant. The pressure is not constant, the volume is not constant, and the temperature is not constant. And because we don't have a constant temperature, that means we do not have a constant change or we don't have a constant internal energy. So to find that change, once again, we use delta U equals 3/2 nR delta T. We can look at the two different states to figure out what delta U is going to be. But let's look at delta U equals Q plus W. Well, remember as we just said, though, in this situation, there is no heat. And if there is no heat, then delta U will only be due to the work. The change in internal energy of the gas is only due to the rapid expansion or rapid compression done on the piston. So if I'm going to look at, let's say, some initial state on this PV diagram, this is an example of an isobaric, isovolumetric, isothermal, and adiabatic process that we could see. So isobaric, always a horizontal line. Isovolumetric, always a vertical line. Isothermal follows really what is a hyperbola here, and on this hyperbola we call an isotherm. That's literally the name of this line. We would say that is the points are on an isotherm, which means every point on that line is the same temperature. And so that, for instance, this is one isotherm. I could have an isotherm up here, which would be at a higher temperature because the pressure and volume are higher, or I could have an isotherm down here, which is lower because the pressure and volume are lower. And then lastly, you have adiabatic, and it's very difficult to distinguish between these two. If you want to know if you have an isothermal or adiabatic process, you really need to, check the delta T, the change in temperature of the gas. If there's no delta T in the process, it's isothermal. If there is a change in pressure, change in temperature, it is probably adiabatic if it has this shape. And we notice that the adiabatic is going from one isotherm to a different isotherm. So this is going from a higher temperature to a lower temperature. If it went the other way, it would go from this temperature to a higher temperature. So while we're not going to do any math right now, I really want to quickly go through what something like this might look like. So if we have a gas or a thermodynamic system starting in state A on this PV diagram, we could say that maybe it first goes under an isobaric, this would be an isobaric compression. Essentially, we would start cooling the gas down, and it would naturally compress, causing the piston to naturally compress on its own. And then let's say that goes to state B, but then we do an isothermal expansion, meaning that we are slowly, we put the whole piston in a heat sink, and we slowly expand it, and while doing that, heat starts entering the system from the heat sink. And then maybe we could even then go from C back to A in an isochoric, otherwise known as an isovolumetric heating process. So we lock the piston in place, we heat it up, and we cause it to gain a lot of pressure. And you'll now see that we went from one state all the way back to itself. We did one process, another process, another process, and we ended back where we started. And this is something called a thermodynamic cycle. So the difference between a cycle and a process is each of these steps. A thermodynamic cycle is a combination of these steps that brings you back to the initial state. Therefore, if we had a system that was somewhat automated, it could continually do this over and over again in a cycle-like pattern. Now, if I'm going to analyze this a little bit, a couple things we want to notice is that because we have the initial and final state are the same, well, that makes some things really easy because that means the change in temperature through the whole process will be zero. And therefore, the change in internal energy of the whole cycle will be zero. That is crucial. We really want to make sure we remember that. Additionally, though, let's look at the work here. If we look at the work, well, this one has no work. It's a vertical line. We could look at the work for the the isobaric process, and that would be this whole area here. And specifically, that would be positive because it is compressing, so work is being done on the gas. But then when we do the isothermal process, well, that would be all of this area, but all of that area would be negative because it is being expanded. It is doing work on its surroundings. So if that's the case, this part here where the red and blue areas combine, well, those parts are going to cancel out. And so to find the work of this entire process, I only need to know the work that is enclosed in this area. So the work is the area enclosed by the cycle. And remember, since delta U is once again 0, that means that if I want to know Q, well, it's just going to be the opposite of whatever that work is. It's going to have the opposite sign. So if we have a thermodynamic cycle, it's going to be going in some sort of pattern where it returns to its initial state. It could be a triangle, it could be a circle, it could be a rectangle, who knows, but it has to return back to its initial spot. And the cycle can either be going in a counterclockwise motion on a PV diagram or in a clockwise motion. And what is the difference between these two? Well, for a counterclockwise cycle, remember that we have this process up at the top. This is all going to be underneath this process positive W, and everything under this process will be negative W. So therefore, this whole part on the bottom would cancel, and we're going to be left with just positive work enclosed in the cycle. So if we have a counterclockwise cycle, that tells us that the net work of the cycle is positive. Overall, the gas is having mechanical work being done to it in each cycle. So the gas is going to gain energy from the surroundings in the form of mechanical work. Similarly, if I have a clockwise cycle, up here I have, this is a minus W because it is expanding. This would be a plus W. So this whole region down here would cancel between the two, and we're left with what's just in the middle, and this would be minus W. So the net work is negative, which means every cycle that the gas is losing energy to the surroundings in the form of mechanical work. So what are our takeaways for these special thermodynamic processes? Well, we want to make sure we can recognize these four: isobaric, isovolumetric, also called isochoric, isothermal, and adiabatic. We want to be able to analyze situations in which we see them and specifically discuss how are these processes physically conducted, how are they accomplished, can we create and recognize appropriate PV diagrams for each one, and can we apply the first law of thermodynamics, delta U equals Q plus W, for each one? Does one factor go away? Do other two factors equal each other? That is where that comes in. And lastly, we want to analyze thermodynamic cycles. We want to analyze these combinations of processes and determine the heat and work based on that area enclosed by the cycles.